speaker, let me introduce our next speaker, computer scientist John Tromp. He will be calculating exactly how many legal positions are there on a Go board.
Okay, we have a bit of a challenge. If I go full screen here, it only shows on my laptop. So I may not be able to go full screen. Hello. Okay. So my name is John Tromp. I am a theoretical computer scientist. Got my PhD in 1993 at the University of Amsterdam. And about 10 years ago, I left academia to work in finance, but I kept on doing Go research as a hobby. And now I'm able to present one of the fruits of that. So this is a talk about how to determine the number of legal Go positions. You can find my homepage at that address, or just Google for my name, and you can also see some of my other research projects. So the topics I will be covering in this talk are, of course, numbers, positions, what is legal, why do I want to compute the number of Go positions. I'll tell a bit about the history of how people have attacked this problem. Then I will, of course, present the main result, what is the number, and show you how the algorithm works that allowed me to compute this. I'll also mention why I am pretty convinced that this result is accurate and how you could verify it. And I'll end with the usual concluding remarks. So, of course, we're all familiar with numbers, the way to count things. But there are still many possible ways to denote numbers. So the normal way we're used to writing numbers is known as positional notation, also known as place value or base B notation. So we're all familiar with the decimal system, where we write 4125 to mean 4 times 1,000 plus 1 times 100, 2 times 10 plus 5 times 1. So the last place just counts the units. This counts the tens, the hundreds, and the thousands. Each place to the left denotes a 10 times bigger value. It works the same with any other base, like computers work in base 2, using just the binary digits 0 and 1. So if you have a binary number 1010, it just means 1 times 2 to the third, 0 times 2 to the squared, 2 to the second, 1 times 2 to the 1, plus 0. So that comes out to 8 plus 2 equals 10. And what will be the most natural base for Go will turn out to be the ternary base, using 3 digits, 0, 1, and 2. So here's a ternary number, 2010, I should say 2010. And it means, of course, 2 times 3 cubed, plus 1 times 3 to the first. So that's 2 times 27 plus 3 equals 57. Now, with the game of Go, we can give a new meaning to the notion of positional notation. We can use Go positions to denote numbers. How does that work? Okay, let's call this Go ternary notation. Instead of the digits 0, 1, 2, we use empty, black stone, white stone. Wonderful. So we can then see an easy correspondence between the first 3 to the n squared numbers, like for n equals 2, the numbers 0 through 80, and Go positions. So these are numbers, and we can write a number 0 in ternary as 0000 using 4 ternary digits, and we just replace them by empty, 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 empty. So 0 is the empty position. Going up to number 1, in ternary that's 0001, and a black stone appears. With 2 you get this position. So all these positions just denote numbers from 0 through 80, this being 2222. Of Of course, we like to write the ternary digits in a n by n square. So numbers and Go positions, pretty much the same thing. Next topic, legal. What is legal? Well, a position is legal if and only if all the strings have liberties. And the reason for this definition is that this corresponds exactly to the positions you can reach in a game, as stated by this theorem. Why is that the case? Well, if a position satisfies this definition, all strings have liberties, that means we can just reach it by fluting all the black stones down one by one, with white passing in between. And then white can place all his stones with black passing in between. So because the rules allow passing, we can put any legal position on the board in a game. And the other direction is even more trivial. If you play a game of Go, then because of the capturing rule, every position will satisfy the definition of legal. Any strings without liberties will have been captured. So let's consider the smallest non-trivial case, 2 by 2. So of course we have all the positions with 4 stones being illegal. That's all these 16 ones. Similarly, the three stone positions where a stone of one color is neighbored by 2 stones of the opposite color are also illegal. And there's 8 of those, because the stone can be in 4 places and it can be either white or black. Any other position with 3 stone is legal, and positions with at most 2 stones are legal. So in the end we're left with 3 to the power 4, 81, minus these 24, equals 57 legal 2 by 2 positions. So we say L2 equals that position, which is just the number 57 written in Go ternary. And it happens to be legal, which is awesome. Of course, for 2 by 2, most positions are legal, so there was a good chance that the number of legal positions itself is legal. Now, the question that often comes up is, do I consider rotations to be, do I count those separately or not? Well, rotations and reflections generally produce different positions. And where this matters is in the superco rule. So for instance, in this case, after black takes here, we allow white to capture here, even though this is a rotated version of this. We don't consider these to be the same. So we allow white capture here, black can capture here, and it's like merry-go-around. And it's not until this point that we say, okay, white, you cannot play here because of superco. That would repeat the position. So symmetries in this talk are just ignored. Yes? White cannot play here because the result would be this position again. The superco rule only says you cannot repeat any previous position. It doesn't refer to, it doesn't care when that position occurred, whether it was 2 moves ago or 5 million moves ago. You just cannot repeat a position ever. Yes, exactly, the whole board position. No, it cannot be. It cannot ever reoccur ever throughout the same game. Exactly. So this is the one and simple rule that makes sure all games are finite. Other rule systems have half measures. Like Japanese rules have one rule that says you cannot play, you cannot recapture directly in a basic ko. Then they have another rule that says, well, if we have a triple ko, then let's replay the game. And then you have millions of other possible repetitions, like the pinwheel ko that doesn't fall into either category. So there, the Japanese game would just happily continue forever. So they have two weird rules that still don't solve the problem. That's why supercode is a pretty cool rule. It just solves the problem directly. A little more about the 2x2 case that is of interesting curiosity. So here I show all the 57 legal 2x2 positions. They are, in this case, this is the only place in my talk where I show some symmetry. So I group them together in rotation and reflective symmetry classes just to make this visible. So I can show a single edge from here to here instead of drawing edges from each of these to wherever it goes here. The nice thing about this is that a game of Go is nothing more or less than a path, than a simple path in this graph starting at the empty position. And we say that the path is simple if it doesn't repeat any vertex. So each node occurs at most once in the path, which is exactly what the supercode rule enforces. And also note that there is no notion in this picture of who is to move. It's just that if you move from the empty position to one of these, it just means that black passed first. So anytime you follow two edges that are both white moves, it just means that black passed in between, and vice versa. So the number of 2x2 games, according to certain rules, you can find on my webpage, is the number of simple paths in this graph. And it turns out to be this number. There are 386,909,593 possible 2x2 games. If you ever want to win a bet with anyone, ask them, what do you think is the number of 2x2 Go games? And then tease them a bit, and then win your bet. Okay, it doesn't quite show. This is the downside of not using a proper full screen mode. It says why. Why do I want to compute the number of Go positions? Well, as famous mountaineer George Mallory said, when people asked, why do you want to climb Mount Everest? Because it's there. So the number of Go positions is there for me, and I want to climb it. I want to know what it is. Most people, when I want to impress the audience with how many positions they are, they will say something like, it's more than the number of atoms in the universe. But that's a horrible understatement. Even the square root of the number of Go positions is orders of magnitude bigger than the number of atoms in the universe. So I want to get rid of this comparison. It's certainly a very, very tough computational challenge. Which is why I wasn't able to compute the number 10 years ago. And we will see later what's involved. And of course, it's the major open problem that was left in our paper called Combinatorics of Go by myself and Gunnar van der Beek from the Computers and Games Conference in 2006. The full paper is available at this URL, or you can just Google search for Combinatorics of Go. It contains a lot of other interesting theorems about games and positions, and I highly recommend that you read it. Okay, now this is what you all came here for. The number of legal 19 by 19 positions is, ta-da, in Go ternary notation. So this position is the number of legal positions, and unfortunately it is not legal. There's stone here and a stone here without liberties. Of course, it was not that likely to begin with. If we take the number of positions and we the number of legal positions and we divide it by the number of positions, 3 to the 19 squared, then you're just moving the ternary point from here at the end all the way back to the start. So you get a fraction. The fraction of legal positions is 0.0000222. So it's almost 3 to the minus 4, 1 out of 81. The probability of getting a legal position, if you randomly color each point empty, white, or black, is about 1.2%. So the odds were against this number being legal. In conventional notation, rather boring, it's this 171-digit number. This is exact, down to the last digit. It's a multiple of 5. I wouldn't show you all these digits if I wasn't convinced that they're all correct. It's amazing that we can compute numbers of this magnitude. Already 10 years ago, I was able, through the mathematics you can find in the paper, to estimate the number as being this. And you can see it matches perfectly for this many digits. Here you have the 9938. That was there around it before. It took 10 years to find all the other digits. So a little history about this problem. Back in 1992, there was a discussion on the Rec Games Go newsgroup, where a German fellow by the name of Achim Flammenkamp was able to estimate the number of legal positions at this 1.2% fraction. So he just sprinkled random Go positions on the board and counted how many of the random sprinklings turned out to be legal. And he found it was pretty close to 1.2%. 2 years later, people started writing programs to do brute force enumeration. Just generate all the possible boards up to a certain size and see how many are legal. Of course, this is severely limiting your size. By about this number, you're already into the many billions or trillions, and this is about as far as you can go. The real breakthrough came in 2000, when somebody by the pseudonym of Les Fables described a dynamic programming method that forms the cornerstone of my implementation. I prepared some bookmarks that actually show all these codes, but considering the difficulty of moving the browser window back over there and back, I'll refrain from showing that. He asked for people to try implement his method because he was anxious to see the results, but it took another 5 years. When my co-author Gunnar Vannebeck had the first program implementing the dynamic programming method and was able to go vastly beyond the earlier result and count all the way up to 10 by 10 boards. Then I came in and I wrote a very optimized implementation using some techniques I will show later that was able to extend it much further, up to 13 by 13. And then with help from my colleague at the Center for Mathematics and Computer Science in Amsterdam, we continued all the way up to 17 by 17. That was as far as we could get in 2006 on the computing cluster. Since then, I've been going around and asking many different places if they could please spare some cycles and a lot of hard disk space and a lot of time to let me compute the next instance. But no luck. I tried my institute, the Amsterdam Computing Center. I asked the Dutch National Science Foundation. I asked Amazon because they have this nice huge cloud, AWS or whatever it's called. I asked IBM, some laboratories here and there, supercomputing centers. No luck. Until 2 years ago, when an astrophysicist called Piet Hut at the Princeton IAS finally offered his services, his institute's computing services to help me out. So I was very glad to take him up on his offer. And I started computing 18 by 18 there. And that finished the next year. And then I made a nice big announcement on a popular forum like Hacker News /dot. And together with announcing the 18 by 18 result, I also said, people, if you can spare more computing power, we can tackle the big one, 19 by 19. So then came forward a sysadmin by the name of Michael D. Domenico at, what do you know, another institute in Princeton on the opposite side, just pure coincidence. He's working at the Institute for Defense Analysis, and they have even nicer computing cluster. So then with joining forces with IAS, we started 19 by 19, and that finished, those computations finished about the end of 2015. But I wasn't able to get the results over because this was on a highly secure network, and they had some goofs where they tried to convert a small number into a PDF file and had trouble getting that out and read back. So it wasn't until January this year that I got the results and was able to reconstruct the number. So about the algorithm to compute this, one major ingredient is the so-called Chinese remainder theorem. What that says is that if you have a bunch of relatively prime numbers, m1 through mk, then you can determine any number up to the product of those uniquely by the remainders. So n modulo m1 through n modulo mk. And I'll show you a small example with just 2 of those m's. So I have m1 equals 5 and m2 equals 8. And of course, if you take 0 mod 5 and mod 8, you get 0 and 0. If you take 26 modulo 8, you get 2. 26 modulo 5 is 1. And you can see that every number occupies a unique cell here. That will be due to the numbers being relatively prime. So if you have, let's say, the number 28, you have an unknown number, n. You want to know what is it. You compute n modulo 8, and you see it's 4. You compute n modulo 5, you see it's 3. Then you can determine it was 28. The nice thing about this is that if one of your moduli is, if one of your remainders is off by a little bit, let's say you computed n modulo 8 to be 3 instead of 4, then when you try to recompute the result, you conclude n was 3 instead of 28. So you see it's a completely different number. So when I use this, and any of my sub-computations, any of my remainders is wrong, I'm very likely to get a completely out of whack result that will be obviously wrong. So here's the top level approach of what we do. We pick a bunch of different small numbers, which we're gonna subtract from 2 to the 64, because our computers like to compute with 64-bit numbers. And I'm going to compute the number of Go positions modulo each of those, 2 to the 64 minus a small number. And when I get all those results, which are shown here, I can use the Chinese remainder theorem and compute my n, which is uniquely determined given the product of all these numbers. So with 9 jobs, I will have about 9 times 64 bits. I will have 576 bits worth of results. And I know the number is only 566 bits long. So that will be enough. You can see where these computations took place. So this is Institute for Advanced Studies. Thank you. And this is the Institute for Defense Analysis. The IDA did 6 of them, and the IAS did 3 of them. And of course, I picked these offsets so that all these numbers are relatively prime. We were running about 3 of these jobs at a time. due to lack of disk space and limited computing power. And when actually I was running 2 at a time at IAS, and Michael was running 3 at a time at IDA. There was also some hiccup where it turned out that many of the files we wrote were corrupted, and 3 jobs had to be aborted near the end and then restarted at IDA. So that leaves the question, of course, how do we compute the number of positions modulo a 64-bit number? Well, instead of counting position by position, we basically count point by point. We count on partial boards that we extend 1 point at a time. So when I take a partial board of just the first I points, it will have 3 to the I partial positions. And I'm going to count those. There will be one count for the partial positions that have no legal completion, so that are definitely illegal. And then there will be other counts for things that can be extended into legal positions. I start here. There is just a single partial position on 0 points, of course, and then I consider all the possibilities for this point. It's either empty, black, or white. So that gives me partial positions of 1 point. And then I take those and I consider the possibilities for this point. So I continue on and on and on until I will have the full counts at the end, when I have partial positions of 9 points, which is the whole board. But if you do this in a dumb way, you're still just doing brute force counting. So we need to be smarter. We need to abstract from irrelevant details. And the irrelevant details for a partial boards of 5 points would be the first 2 points. I don't want to know what those first 2 points are. I'm just going to care about the last n points, in this case, the last 3 points. So what all these 5 positions, partial positions, have in common is that the last 3 points are a white stone with liberties, an empty point, and a black stone with liberties. Similarly, these are all the 4 positions that can be summarized as the last 3 points are a white stone without liberties, then an empty point, and then a black stone with liberties. I don't care how it is that this white stone lost its liberties, whether it's 2 black stones here or a white stone and black stone here. It shouldn't matter for how I'm gonna make this into a legal position. Finally, for the points without liberties, I do need to know how they are connected. So in this case, I end up with a libertyless white stone here and the unconnected one here. Whereas in this case, I have a libertyless white stone here and here, but they're connected. So I need to know, I need to remember these are connected. Any questions so far? I'm sorry? Connected. So I'm abstracting this partial position into this like abstracted version, where I just remember that there is the last 3 points of the partial position are a white stone without liberties, another white stone without liberties, and a black stone without liberties. And I'm remembering that in this part that I'm forgetting, there was a connection, formed a connection between these 2 white stones. They're part of the same string. And as I mentioned, my implementation had some optimizations. The major one is this. I found a way to encode these abstracted states very efficiently. So if these are the last 8 points of some partial boards, so there's a black stone here with liberties, and then there are all these stones without liberties, and I know that one is somehow connected to one here. These 2 and 3 are by themselves, and these 4 are somehow all connected. The way I can represent this is like this. For stones with liberties, I still remember their color, but for stones without liberties, I just mark them, they're all gray. I don't know their color. What I do know is if they're connected to some other stone to their right, and whether they're connected to some other stone to the left. So from this, I can reconstruct the full details of that one. What I do is I infer the string connections from the left and right flags. So actually, there's a slight mistake. This arrow here should be on top of this stone. So given that this arrow is here, this stone points to the right and this stone points to the left, I know these two are connected. From the fact that this points to the right and this points to the left, I know these are connected. So now these are all connected. Then from the fact that this points to the right and this points to the left, I know that these are connected. I'm making use here of the fact that connections cannot cross. My go position is planar. So any connections have to necessarily nest. They cannot cross. That's what allows me to infer these connections. And then I can infer the color. If this is a stone with liberties, then of course this stone cannot be black. It would be neighboring and it would also be sharing in the liberties. So this one must be white. From the fact that this is not connected to this, I know that this is again black. This is again white, and these were all connected, they're all black, and then I know that one is white. In the actual representation, there's also some normalization happening. In the end, I only need three bits per point. So because these states are only 19 points long, I can fit the whole description into 57 bits. Again, fitting nicely within the 64 bits that a computer likes to deal with. However, there are still a lot of these possible what I call border states. In fact, for 19 by 19, there are over 363 billion. So that's how many counts I have to maintain. It's what the last slide showed. So the color of the last n points, whether these stones have liberties and how the libertyless stones are connected. All that information together is what I call a border state. It's like the state of the border of a partial position. The information I need to determine if I can complete it into a legal position. So one state, together with a 64-bit count, will take me 16 bytes to store. A whole set of partial board counts therefore takes 5.8 terabytes. This is not going to fit in memory. I'm going to have to store all this state on a big disk. I can optimize a little bit, because if I have a full such set of data with increasing states, then I don't have to encode the full state. I can just encode the delta difference between successive states. That allows me to save a little bit. But still, I'm going to be producing these border states at different points in the computation, and I will not always be able to recognize when I generate the same border state again. So sometimes I will generate the same thing multiple times, like about between 1 and 3 times on average. So that is some redundancy. Still, on average, I will be using about 4 terabytes per data set. So the idea is to store all this data on the disk, representing the counts of all partial boards on a certain number of points. Then you read in all this data, you consider the possibilities for the next point, empty, white, or black, and that lets you generate the next data set. which you will be writing out to disk. And you can let a whole bunch, multiple CPUs cooperate to do this in parallel. Partitioning is a little tough because if you look at this encoding, and here are the first, let's say the first 9 bits of an encoded border state, and vertically you see how many border states there are with those initial 9 bits. You see it's a very uneven distribution. I cannot just divide this equally into 16 parts if I have 16 CPUs to work on the data, because one CPU is going to have a lot of border states to deal with and some is going to have almost nothing. So there is actually a separate problem of dividing the encoding space into parts that have equal numbers of border states. That's a whole separate dynamic programming problem. That's the most complicated part of the algorithm. But that's solved. So here's an overview of how the computation takes place. So I have my disk space, and this is going to be one data set. I've already divided it up into 4 partitions. So there will be 4 CPUs working on these separate parts. For each CPU, what you're looking at is a bunch of files, each file being a sorted sequence of these pairs of a state and a count. What the CPU is going to do is it's going to read all these files in parallel, and it's going to merge the state pairs, and it's going to compute the successors. So somewhere in this process, it will determine that, okay, the next state from this file is S with a count of C2, and this file has the same state in a pair, S with count C1. Because these states are the same, they have to be combined. So it's really a single state where the new count C is just the sum of these two. And from this, I can generate 3 successors. One for the case that the next point is empty, one for the case the next point is black, and one for the case that the next point is white. There's some obvious way to update these state borders to compute the next one. So then in my memory, I accumulate these successors. I say S1 has a count of C, and I have an S2 with a count of C and an S3. And this is ultimately, when your memory fills up, you will sort all this data by state, and then you will again use your partition table to partition it for the next round. And you will write parts of your memory into a file that will be handled by this CPU, and a file for another CPU, and for the last 2 CPUs. So then your memory is all flushed. Then you can start over again, just continue there. And every time your memory fills up, you will produce a set of files. And this will go on for like thousands of rounds. And at the end, you've consumed all this data, and you've computed the next data set. So this data set corresponds to some number of points on the board. Let's say the first 17 points. And this will then be the counts of all partial positions on the first 18 points. So you need to iterate this whole process for 19 times 19 times. It's a lot of I/O and a lot of cycles. If you want to repeat one of these computations yourself, you can get the software from my Git repository over there. You will need some serious hardware. I suggest you have about 15 terabytes worth of fast disk space, about 8 to 16 cores, CPUs, a healthy amount of RAM. If you have too little memory, then your memory fills up pretty quickly, and you end up having to write these files a lot, and then you end up with like 10,000 files, which is too much to be reading back all in parallel. It becomes too inefficient. But this is a good, healthy amount of memory to work with. And you need a few months of running time and a lot of patience. The software uses additional checksums on all the files. So if there were some error reading back a file that wasn't detected by the hardware, then I would still see the failing checksum. I check that all my counts sum up to the proper value 3 to the I. Of course, 3 to the I modulo my 64-bit modulus that I happen to be using. And another good check is that earlier, when I was computing, let's say, 13 by n boards, I didn't stop at 13 by 13. I continued to also compute 13 by 19. When you're computing with a width of 13, and the data sets are much smaller, so it's much easier to compute the result. But then when you get to 19 by 13, you can check that you get the same result. These are computed in quite different ways, but they have to match exactly, of course. But the most important check is that your results match what you can accurately estimate from earlier results. I will show how that works. So in our paper, we mathematically derived that the number of legal positions on an n by n board should behave like this. This is subject to some conjecture about vanishing error terms, which we haven't been able to prove. But the data looks like this should hold. So there's one normalizing constant in front, and there's some constant to the power of n plus n that more or less accounts for the effects along the border. The most important term is this, because it's to the power of m times n. So this is the big number. This is 361. And L is what I call the base of liberties. So if you ignore legality, then your number of position grows just as 3 to the n squared. But requiring positions be legal makes this constant a little less than 3. It's 2.9 something. And we'll soon see how accurately we can estimate L. So this notation is just saying that if you take this for increasingly large values of m and n, and if you take this and you divide it by this, then that will converge onto the value 1. So one way to obtain L is as the limit of a count of n by n, count of the slightly larger square board, and then divided by the square of this count, which is a slightly off square board, like an 18 by 19 board or a 19 by 20 board. And given L, we can in turn solve for B and then for A. So what I did is, whenever I got a new result, I improved my estimation of L. And the results are as follows. If you've only computed up to 3 by 3 boards, or actually up to 4 by 4, then you compute this approximation of L. By the time you get to 9 by 9 boards, you already compute this approximation of L. So it's amazing how quickly the accuracy improves. It's very, very fast convergence. So already 10 years ago, using our results up to 17 by 17, we could compute this very accurate approximation, which is what allowed us to have this estimate of L19. And now with the latest results, we have this final approximation of the base of liberties. So it's like a mathematical constant that just expresses the restriction of legality. Yes. This depends upon a conjecture. So there is, yeah. If you write this, if you want to write this with an equal sign, then there's some error term in here. So it says it's this times 1 plus some error term. And the conjecture says how fast we think this error term goes to 0. Oh, this I copy and pasted from different places. So this should be beta, this should be alpha. Yeah. I use both alpha and capital A to denote this one thing, and both beta and B to denote the other one. Yeah. What is the, oh, yeah, this, I tried to cut off each line at the point where I deemed the representation to be accurate. Either I cut it off one digit too early, or it really took one more step to realize that this digit should be a 3. Yeah, that looks suspicious. I'll check that. Yes, that's a separate theorem using a version of the so-called Fackett's lemma. You can prove easily that taking the n squared root of the number of legal positions has to converge to a value L. And this is pretty convincing evidence that it's this value. Conclusions. We used a technique known as dynamic programming to reduce a problem that looks to be exponential in n squared, which would be counting positions by brute force, which would be totally infeasible, to a problem that's exponential only in n, which is just barely feasible. This is quite analogous to the problem of factoring. If we were to factor L19, if you use the dumb method of trial division, your factoring time will be exponential in the number of digits, in 117 digits. So you'll never finish. But using advanced factoring algorithms like the general number field sieve or the elliptic curve method, those are only exponential in the square root or in the cube root of the number of digits, which make it feasible. In fact, the paper has a complete factorization of L19 that I computed with the elliptic curve method. So that's quite analogous to the advanced algorithm for counting. I answered the ultimate question of liberties, the universe, and every string. And this is the latest version of the approximation formula. So we can say that the number of legal positions on an n by n board is accurately described by this formula. So if you plug in 100 by 100, you will get something that is amazingly correct, like in the first 15 digits. And of course, Go counting turns out to make a nice server benchmark. The algorithm. Okay, so alpha is the pure constant factor. This is alpha. And this is beta. Beta is raised to the power of n plus n. This is the base of liberties, the most important one of these constants. As I was saying, the algorithm is an instance of what is known as MapReduce, which is widely used in Google. This is a classical MapReduce problem. And actually, a lot of data centers spend a lot of computing power on solving MapReduce problems. So it requires a good balance of memory, multi-cores, multiple CPUs, and disk I/O bandwidth. And this computing challenge, which you can extend to even bigger board sizes, makes a very nice family of benchmarks. The code is very small, but the computations are very big. So we were able to count Go accurately. So people ask, what about other games? What about chess? The king of games versus the game of kings. With chess, there is no hope that we'll ever get an accurate count. And the reason is that even determining if a single chess position is reachable in a legal game is a very tough question, arbitrarily hard. To wit, look at this position. Can we determine whether this is a legal chess position? Can we reach this position? Well, you'll notice the black king is in check. The white bishop could not have moved here. It also didn't just promote, because this is on the side of the board. So something must have moved out of the way here to give check. It looks like the white king maybe just moved out of the way, but then the king would have been in double check by the rook and the bishop, which seems impossible to reach. Most people would conclude this is not legal. Actually, it is legal. You have to know some fine details of chess. So you're saying somebody made a stupid move? Yeah. The way you can reach this is if you start with a white king here. You start with a black pawn here. You start with a white pawn here. And then this black bishop moves from somewhere over here to put the king in check. The king is not yet in check from the rook because there is a black pawn here. Then white moves his pawn from c2 up to c4. And there's a rule in chess that if a pawn moves up 2 spaces next to your pawn, you can capture it en passant. So the en passant capture both removes the black pawn from here and the white pawn from here, which produces this double check on the white king. And then the king captures the pawn here. So given the difficulty of determining if a single chess position is legal, and there's a whole field of problems devoted to this. They're called retrograde problems. People have written books about this. One famous author is the logician Raymond Smullyan. Lovely problems. But we're not going to be able to count the number of chess positions. We're going to, at best, be able to approximate it, which is one of the things I'm still working on to get better bounds on the number of chess positions. Yeah, so this is some more points about why this might make an interesting benchmark for servers. Each time you go up 1 step in the board size, it becomes 5 times more effort to obtain the count. That's why it took 10 years after doing 17 by 17. Oh, that's the last slide. Any more questions? Yes, it's not until you study the number of games that the details of the rules become very important. But all the rule sets agree on what is a legal position. Actually, that's not quite true. There are rules where you cannot pass, where you just have to play a stone at each turn, and the first player who cannot place a stone loses. I think they're called stone rules. So there you actually have a different notion of legal position. For instance, I can show you what. Going back, if we go back to the 2 by 2 positions, I believe this is not a legal 2 by 2 position with stone rules. There's no way for y to end up with a single stone. But I have the number of 2 by 2 games, which you saw was this insane 386 billion number. That's the limit of what you're going to be able to compute. If you go up to 3 by 3, we can only wildly estimate the number of games. It's about, I would say, 10 to the 5,000. I'm pretty sure it's between 10 to the 4,500 and 10 to the 5,500.
We are going to take the last question. Sorry for the time.
Yes.
You mentioned the 1992 estimate of Flammenkamp,
Yes.
Achim Flammenkamp, and you said it was 1.2% of 3 to the 361. How accurate was that? Because I can't compute this by heart also.
That is very accurate. If you go back to this exact count here. So this can be considered the fraction denoted in Go Ternary. So it starts out 0.0000222, and like I said, this is very, very close to 3 to the power minus 4, 1 over 81. And 1 over 81 is very close to 1.2%. I think it may even be 1.20 or 1.21. So yeah, the 1.2 is right on the mark.
Thank you, John. Thank you very much.